Hello and welcome to this video which concerns scaling SQL Server in the cloud and specifically using Microsoft Azure. And the reason I've made this video is partly for my own benefit. So I was doing some research on using SQL Server in the cloud, what kind of options there were for genuine elastic scaling. This idea that you can kind of automatically scale something out as needed, either due to short-term peaks in demand or even just generally over time as the data grows to provide that kind of increased throughput. And I found a lot of the information on Azure quite confusing. There was, as with most of these companies, a lot of documentation. So I've been digging through it and decided to put this video together to hopefully save you guys some time if you're trying to ask the same question about how we do this. So a little bit about me. My name's Luke Briner and I live in Cheltenham in the UK, and I run a company called Cotswold IT Consulting, and we are a cloud and cyber security specialist, but also other kind of business consulting and things like that. So this video is kind of related to one of the projects I'm currently working on for a customer. I'm also the ex-CTO of a software startup company, so I've used Azure a great deal over the last 6.5 years, used very many of the resources available on Azure and have kind of seen it grow and develop over time. So I'm very happy to kind of recommend it as a supplier. I'm happy that it's kind of reliable, it works, it's pretty good value for money, and particularly for the Microsoft software houses of the world like we were, Azure just fits really well. So that's kind of why I've gone down this route for this video. So let's start by just very briefly kind of give a bit of background about what we're actually talking about here. So we're going to start by looking at SQL Server itself. And this is most of this you hopefully already know, this is a Microsoft relational database engine. So we're talking about a database that has relationships between different tables, and the relationships between the tables allow us both to enforce what we call referential integrity. That means if a user belongs to a customer and that customer doesn't exist, then the database can detect that that user points to an invalid customer, and it will either allow you to kind of ignore that problem or it'll allow you to cascade the deletion of one item to delete all of the child data belonging to that item, and just a number of other features like that. So this is really certainly traditionally the main go-to database for business applications. It's used pretty heavily in the world of web applications. And of course, although we're talking about SQL Server, there are also other relational database engines like PostgreSQL and MySQL and Oracle and others like that. So SQL Server is certainly not the only one. First released amazingly in 1989, and we're now up to version 2017. Now, in general, SQL Server has been Windows only, although now from versions 2017 onwards, Microsoft have made efforts to also make it compatible with things like Red Hat Linux. And I'm not sure how many of the features are available on Linux and how much work's kind of been done with that, but I know that they now support Linux as well as Docker, so some more deployment options. There are various editions. The Express edition is free to use, so it's good for people kind of new to databases just wanting to have a play, or people who are kind of just doing stuff at home and not doing things commercially, right through to the Enterprise edition, which is incredibly expensive, very powerful, and has lots of kind of database features. The licensing of SQL Server, this is a proprietary product. It's not open source, and although the Express edition is free to use, there are certain licensing constraints on the higher editions of it, and I mean you can be paying $30,000 for an enterprise license, so we're not talking cheap, but obviously for these kind of large enterprises that's kind of small money for something that's as kind of proven as SQL Server. And I thought this was quite interesting. It supports up to 524 petabytes of data. So a petabyte is 1,000 gig. So this is 524,000 gig. Oh, sorry, 1,000 terabytes. That's 524,000 terabytes of data, which is crazy. 12 terabytes of RAM, 640 CPU cores. So there's no real problems with an individual SQL Server instance scaling. Obviously here the issue's down to the hardware that's actually available to you. So SQL Server, when we're running SQL Server on the cloud, Azure provides a couple of models. They provide effectively a platform as a service model where you're really paying for utilization. So effectively for the number of kind of database transactions, the number of operations that you're doing, you get charged a certain amount of money. And so for, fairly consistent usage, that can be quite cost effective. If your usage varies a lot, then that can be quite restrictive because you're going to kind of have to pay for your worst case usage. A newer feature is something called the vCore model, so a little bit closer to what you traditionally have, where you're paying pretty much for a whole virtual machine based on a number of cores. That obviously can be useful for enterprise customers because that allows you potentially to match what's on the cloud with what you have maybe currently on premises so that you're going to get similar performance. Amazon Web Services provides a single instance model, so they don't really do anything particularly clever. One of the difficulties when you navigate the cloud is trying to read through the kind of marketing information to say, well, what actually is this under the covers? And in terms of AWS, it's pretty much SQL Server hosted for you on an Amazon instance with a certain amount of RAM and cores. They do some of the work for you, like software updates and things like that. I think it has failover built in automatically. Doesn't really give you a lot of bells and whistles other than that. And Google Cloud provides a single instance model, but they do provide the ability to configure failover. So my understanding is Google has a fair few more options than AWS, but still a fairly simple model compared to what's available, unsurprisingly, on Microsoft Azure. So one of the questions we might ask is, why the cloud? Is this really relevant to me? If you're an enterprise customer, you already have a database server on premises, it works. What's the problem? Why should I use the cloud? And there are a number of reasons why you might use them, why you might decide the cloud's the right thing for you. So one of them is pay-as-you-use pricing. So if you've got something you need to carry out temporarily, for example, rather than having to buy or utilize a server from someone else, you've maybe got to get that server, set it all up, run something for 2 hours and then kind of give it back again. You can do that very, very easily and relatively cheaply on the cloud, because if you run something for 2 hours, you basically pay for 2 hours. So that's quite cool. Prototyping stuff, again, if somebody says, I want to find out whether Active Directory is a good idea, well, you can set up an Active Directory on Azure. You can have a play around with it. If you don't like it, you can delete it, and it might have cost you $5. So that's kind of a big plus, I think, for the cloud. The other thing that kind of makes a difference, and there's going to be different companies with different requirements as regards to infrastructure management, but if you're a new company, particularly, you don't have a server room, and you're considering setting one up, well, that's going to cost you a ton of money in terms of air conditioning, in terms of dedicated room, perhaps physical security, redundant power supplies, redundant equipment, redundant internet links, all of those kinds of things. So by using the cloud, as with any hosted provider, you're effectively transferring that management and the cost of that to somebody else. In some cases, you might only be transferring a portion of that, because you might still need some things on premises. You also, as a kind of a result of that, is you get to reduce your internal support headcount. So having all of your servers on premises is going to require perhaps 10, 20, 50 people all on a large team just to cover the support of that equipment 24/7. That's a lot of people, that's a lot of salaries, a lot of pension contributions and tax payments and everything else. So again, transferring that to a cloud provider or hosting provider means that you could either have a smaller support team or even potentially no support team. You could just maybe do third line support as and when you need to. Hardware and software upgrades, you're all getting that. That's included in the price. So rather than saying I've got a server that's going to maybe last 5 years, at which point I have to replace it all, and having all the kind of hassle of upgrading software, operating systems, patches, everything else, all of that's obviously included. It's quite nice. they're already globally positioned. So if you're a company that's looking to take over the world, sure, you could move to Japan and build a kind of a data center, buy an office somewhere, build a room, and everything else. Again, is going to cost you several $100,000 plus to do that. Whereas here, the cloud provider, any hosting provider, they've usually got centers in perhaps 10, 20, 30, 40 places around the world. A lot of it was written initially around automation and kind of DevOps, and that's partly because the infrastructure needed for the cloud providers to actually run their systems itself requires a lot of automation. But what that means is they are therefore able to expose some of that functionality to the customers and say, well, if you want to create a database, you can do it manually, or you can just call this a web endpoint from a DevOps tool from Jenkins or GoCD or something, and have that database automatically provisioned for you. And it just saves the time, the physical time that normally be involved with you having to do that yourself or writing it all manually. Because although you can automate things on on-premises servers, the tooling required to do that varies massively. I remember writing a script myself to actually process a backup database from online and bring it down and unpack it and restore it to a local server. And that was a relatively large amount of work to kind of develop and debug that. And over time, as things changed, I had to keep upgrading the code. It's that kind of thing that you just goes away when you have all this automation built in. Another thing is you're getting top level infrastructure, so you can kind of go out there and buy your own network switches, but are you going to be able to afford to be buying Cisco switches, or are you going to be buying some cheapo thing because network switches are actually expensive, or hardware racks are expensive, all of these things costing thousands and thousands of pounds. And of course these guys, they're already using top level infrastructure because they're providing a service and it needs to work, so you're getting quality. And obviously, in most cases, this is kind of what we're really getting to, is this idea of easy and quick scaling, particularly for web applications. The main selling point of the cloud is I click a button, my application scales up, and I can handle a lot more users, a lot more concurrency. There are, surprisingly, reasons why you might not want to use the cloud, and these will, again, depend very much on your enterprise, your risk appetite, your kind of finances. If you already have servers and you're using them, you've already got the aircon, you've already got the backup power supply, you've already got the room, etc., then clearly there is some mileage in utilizing that equipment rather than scrapping it. So in some cases that might just be cheaper or easier. If you've got an existing system that's been running for 20 years, well, do you really need the hassle of moving it to the cloud? It's probably not really worth it if that's already set up. If you require more direct control, so one of the difficulties you have with the cloud, or again, any hosting provider, is if that service goes offline for any reason, you're kind of trusting the hosting provider to get it up and running as quickly as possible. Now, they're going to employ good people, they're going to know what they're doing, but they also have a very large problem that's not necessarily very quick or easy to fix. So one example of that is a network switch patch that was rolled out, and the problem with the patch was there was a bug in it that then meant it kind of spread a little bit like peer-to-peer around all the network switches. It caused the network switches to stop working, but by kind of pushing another update to try and fix that, the update was then getting overwritten by the old patch because of this kind of peer-to-peer mechanism. So that took, as I think, about 12 hours to kind of understand and kind of get to grips with. And of course, if you're an enterprise, 12 hours is a long time to lose business for. So are you going to be able to do that better yourself on your own equipment? Well, you're certainly going to have more visibility of it. So potentially you might be able to make that work better. Obviously, if you have very specific hardware requirements, I'm thinking military spec, that kind of stuff, then you might not be able to get that on your cloud provider. You might, but you'd need to check. If you have regulatory requirements that are not met in the cloud or not obviously met in the cloud. So these cloud providers do go out of their way to get accreditations and get kind of auditors to come in and make sure they're doing things properly. But depending on the kind of regulations you have, you still might not be fully convinced of a cloud provider. And a good example of this was when Microsoft were taken to court by the FBI wanting them to hand over data that was in their island data center And because Microsoft were a US company, there was a question of whether they could be forced to hand over that data as the owner of the infrastructure, even though the data itself resided in another country. So depending on what you're doing, those sorts of things might be an issue. There's also this strange danger that people kind of think, well, this is really easy to do, so actually I'm going to be spinning up a load of machines and just doing stuff because it's so easy to do. Click a button, wow, I've immediately got a massive database server. But if that's, it might only be costing you $50, but if that's happening frequently and you're getting all of those $50 adding up, then you could end up spending money that you wouldn't have traditionally spent if somebody had to go through the process of getting sign-off on a new physical server. So bit of kind of swings and roundabouts on that one. And the costs can grow quickly if you don't select the services correctly. So this is something to think about. If you, say, spin up a load of databases and you put them on a certain tier that costs you, let's say, £100 a month, and you don't realise you're only utilising 25% of that capacity, then you could be spending several £1,000s a month on things that you're simply not using. And the per unit costs are relatively high because of all the included services. So those costs can grow. You do need to think about how you're going to monitor the utilization and make sure that you're not spending what you don't need to spend. So let's start by kind of looking generally at what we mean when we're talking about scaling a database. So like all IT systems, databases are constrained by server resources. And that's the same whether they're virtual or physical. They have a certain amount of RAM, of CPU cores, of CPU speed, of kind of disk input-output speed, network, either speed or bandwidth. So a number of things that are going to constrain that. There are potentially other resources as well, server connections, threads, processes, whatever it is that's constraining your application. There are just certain things that are going to mean that database can only go so far. So the maximum capacity of the database will depend on the actual application, but realistically, we could be handling perhaps several thousand concurrent users quite easily on a single database, and for many applications that might be more than enough users, because remember that in most cases the actual database number of database connections is usually a lot lower than the number of users on a particular web application at any point in time. So somebody navigating a web page doesn't necessarily cause another database request, especially if you're using caching. A lot of that stuff's going to come straight out of memory on the web server. So maybe your database can handle 1,000 concurrent connections, and that might equate to 10,000 concurrent users. So you've got kind of quite a lot of scope here. But obviously in other situations, the actual maximum capacity of that database might be much lower. So if the database also performs a reasonable amount of processing, so if you're doing a lot of joining, a lot of complex queries, big kind of where clauses and all kinds of stuff, then your database could end up being kind of run inefficiently. So clearly it's going to run out of connections, it's going to run out of capacity quicker or sooner rather than later. So disk I/O kind of used to be a bit more of a big deal. With solid state disks, then that's kind of leveled out a little bit more, and you're probably just as likely now to be getting bound by CPU or RAM as much as you are now on disk I/O. And network I/O kind of just depends really on the sorts of data you're pushing and pulling on your system. So the obvious way to handle a larger load is to scale up, and that's the phrase you need to know. Scaling up is basically, let's put more RAM in the machine, let's put more CPU cores, let's give it more network I/O if that's even possible. And on the cloud it's no different. If you scale up on the cloud, AWS, Google or Azure, anyone else, you pretty much find your resource, click on it and say, right, I want to take this from level 6 to level 7 or whatever it might be. And there's usually a selection of different types of machines. So you might have RAM heavy machines or CPU heavy machines, depending on what you're doing. But effectively, you just crank up all the hardware. And obviously, if your limitation is RAM and you put more RAM in it, then you're going to raise that performance level until the next resource that then hits the limit, whether that's either more RAM or whether it then starts becoming CPU bound. The difficulty, of course, you get is at some point those larger machines can become disproportionately more expensive depending on your provider. So all of a sudden adding 20% more resources might cost you 50% more money because you're starting to move into specialist areas, or the next size up happens to be another 16 cores even though you only want another 2. So there's going to be a point where the cost effectiveness potentially is going to start to suffer. And of course, the other thing is at some point there is a maximum size of machine that you can handle, whether that's on premises or on the cloud. At some point, you're going to be on the largest machine. And if you're still struggling at that point, then there's nowhere else for you to go. The other consideration, of course, is that it's not just your general kind of loading of the application. Really, you need to size it for your worst case, because you might be handling, let's say, 5,000 users on average during the day, but maybe at peak you're handling 50,000 users, and you can't have the system falling over as soon as you hit that peak. You need to be able to handle the peak, and you might be spending a lot of money handling the peak, even if your average is not actually very high. So at this point, you kind of need to scale out, and this is really what this video is investigating. So our first option really, or the first thought that some of you might have, is about this kind of idea of failing over, because even if you've got a nice super beefy database server and you've given it 50 terabytes of RAM or whatever, you've still got to consider availability. So even if you've got that peak service capacity, you can handle your 50,000 users, you're still going to probably need to scale out for availability anyway, even really early on in your design. And the first of these is what we would call a failover system. This comes built into pretty much every relational database engine that there is. And although it doesn't add capacity because the failover server is not in use in normal running, but it continuously gets synchronized to the master. So every time something happens to the master, the transaction log gets sent over to the failover, and the failover applies all of those changes to itself. So they're generally always pretty much in sync. And the point being, if the master ever goes down and the server, the monitoring service detects that, it will simply switch over to the failover. And depending on how you've got that set up, it's up to your application to either deal with that itself or to use some kind of DNS mechanism that will work automatically, so that all of the applications now start talking to the failed over system instead of the master. So unfortunately, because in most cases in the basic setting of this, the failover is completely passive, so you can't connect to it. So this doesn't give you any extra capacity, but it's really kind of the first kind of way of thinking of scaling out. And you kind of want this anyway. You should always have a failover system for your database set up, just because in most cases anyway, the risk of your service going down for any particular period of time, if this is your product particularly, is kind of a bit of a showstopper. You're going to lose business. You're going to annoy somebody who's going to say, well, I know it's not your fault, but you took too long to fix it. So get your failovers on, but it doesn't really solve the problem. So the second method, which is really a nice go-to method because it's generally really easy to do and it gives you extra capacity. However, it only gives you extra read capacity. And that's the significance of this model, what we might call read-only replicas or kind of master-slave architecture. And the theory is very simply that all of the writes or the updates or the deletes go to the master database, and that needs to be handled in the client library somehow. So obviously the client applications or the library in the web applications needs to know whether it's going to connect to the master or to the slave. And usually most libraries will allow you to do that by specifying a flag that says this is a read-only operation or this is a writable operation, and it will be directed accordingly. And the way Azure supports this is a screen called the geo-replication screen, which we'll see in a second, which allows you up to 4 read-only replicas. So it's kind of limited, which is a bit annoying. If you're creating a global application, 4 replicas is not really enough, not really anywhere near enough, in fact, especially if you want to co-locate one of them with the master just to give kind of local read capacity and allow the master only to be used for updates and for writes. So that gives you 3 locations globally, which is kind of a bit rubbish. What it does provide, however, is automatic failover. So Azure can detect when your master database goes down. It can choose one of the slaves to become the master, and then it all kind of automatically updates. Again, your client application needs to know how to cope with that and should ideally use retry logic to, as far as possible, transparently deal with that. But in worst case, it might take up to a minute to completely fail over, in which case some customers are going to see errors potentially. So you kind of need to consider that. But the nice thing about this, like I say, is it is very, very easy to do. The other thing with this, especially when you think of global replication and in fact any replication mechanism, is you've got to start thinking about the balance between the performance of writing to a database that then synchronizes to another database, or the data integrity of doing that all synchronously. So you can send let's say delete a row in the master, and you can immediately come back and say, right, I've done it and I'm going to carry on. But of course those slaves could take a reasonable amount of time, let's say a few seconds up to maybe 20-30 seconds, maybe worst case, at which point those slaves are all going to have stale data. And if your web application relies on that data being up to date and you've updated something asynchronously, you're going to have a problem. So you need to think about those kind of designs. If you say to the master, well, you need to replicate this synchronously, then clearly you've got to wait that period of time when you hit delete. You might have to wait the 30 seconds before it comes back and says it's correct. So you're probably going to have a combination of both of those. You would allow some data to be asynchronous, but one of the most simple gotchas is calling a write operation immediately before calling a read operation, and kind of expecting the data you've just written to be available to come back. And of course, it's not going to be if you do it that quickly. So it brings in some issues, and it does give you the extra read capacity. It doesn't really give you any particular elastic scalability. And like I say, in Azure, you can only have up to 4 read-only slaves, which I think is a limit of SQL Server rather than Azure, anything particular about Azure. And Google Cloud, interestingly, supports a manually configured equivalent of this, so you can kind of set up those slaves. But I don't think AWS supports anything other than simple failover. So Google Cloud's kind of got something, but Azure, like I say, has got this. So this is kind of limited. Like I said, only gives you read capacity. That's the kind of the big stinker, and all of the writes still have to go to a single server. The screen kind of looks like this. So when you go into the geo-replication screen in Azure for your database, you'll see the primary database at the top there on the top line. And all you have to do is click a button. So I click the button for West US. And what that happens is it will initialize, effectively create a new database in West US. It will ask you for a database server to create it on. And you'll have to create a server if one doesn't exist. And then it initializes. Once it's initialized the setup of the database, it will then say seeding, just while it's copying the initial data across. And then once that's happened, status goes to readable, because these are read-only replicas. And it's kind of easy to do, quite nice, but again, fairly limited. So an alternative which isn't really designed for the same use case but might be useful in some architectures and is probably worth considering is something new called Azure Data Sync. I mean, I say new, I think it's probably 6 months old by now. And this is kind of slightly lower level replication. So you've got more settings, more configuration to do, but it does give you some more features which might give you some flexibility over the read-only replicas that might make this a solution that you can use. And effectively it supports a hybrid of cloud and on-premises databases, and effectively has the concept of a single hub database, a bit like a master, and then some member databases which can be cloud databases, can be on-premises, or a combination. It doesn't have to be both. And there are certain limitations on how many cloud databases you can connect to it, but you get more control over what's happening. So for a start, you can have bidirectional replication, which you can't on the previous slide. So this allows changes to be made to one of the member databases to be reflected back up into the hub, and then for the hub to reflect those down to the other machines. You can also choose a subset of data, so you don't have to synchronize everything in the database. You could say, well, there's just one table that I want to synchronize, and everything else can just have a local copy, so you could do that as well. And the other thing that can be quite useful is you can set how frequently this thing synchronizes, and you can set it down to as low as 1 second, which is obviously kind of pretty extreme. But again, for kind of batch processing and stuff, you could say, I want you to do it every 2 hours or once every day or whatever. So kind of quite cool. Like I say, it works with on-premises as well, although the on-premises databases, as you might imagine, take a bit of setting up compared to doing it in the cloud. But is that going to give you the right flexibility? There's some kind of replication conflict handling, but the choice is basically, does the hub win or does the member win? They're your choices, which is kind of a little bit of a blunt kind of option, but there you go. It does raise up the question of designing your databases to replicate properly. Every time you have replication, you need to think very carefully about your choice, particularly of primary keys. Numeric primary keys don't work when you have multiple masters, because you're going to end up with the same primary key potentially in 2 different databases which refer to 2 different sets of data. And so when they come to replicate, they look like they're the same thing, but they're not. So you can't very easily deal with things like that. So it's a replication option. It kind of might work on a lower level, but with the restrictions and with some of the complexities, not really what we're looking for. So we're really kind of talking here about what's this problem with scaling out? Why does it seem to be so hard to scale out? Why is it that even Azure don't have a switch that we can flick and say, right, I want you to grow out to 50 databases and I just want it all to work automatically? And it's kind of an important question, because if we don't really understand why it's so difficult, we perhaps won't really understand how to solve the problem. I mean, at the moment, if I said I want, 10 times or 100 times the database size or scale of what I have, it's quite simply not possible automatically. And the issue here is we have a conflict between relational databases and scalable databases. So if you want SQL relations, which we do because we're using a SQL database, you either get network latency because you separate the data, you cross-join servers while you're doing your data queries, and you incur all of that network latency. Or the alternative is you duplicate all of your data across all the servers, which is great, but then when I update one database, I either need to wait to update all the other databases, or I risk having stale data on some of the replicas while that process takes place asynchronously. So you've got a lot of things that you're kind of playing off here. If you want the extra throughput, but in both of those examples, the servers end up talking to each other anyway, then you're not going to get any extra throughput. So in the first example, those kind of cross-server joins, well, it means when I'm querying one database, it's actually going to several others anyway. So I'm actually querying maybe 4 or 5 databases. So I'm not getting the idea of kind of multiplication of scale out. And likewise with the second one, if I have to synchronize all of those, then again, I'm not hitting one database, I'm hitting all of them every time I do anything that updates the data. And asynchronous, again, just brings me that kind of stale data problem. So in other words, in order to increase throughput, what we want to do is we want request number 1 to go to a server, request number 2 to go to a different server. That's kind of where we get our scale out capacity. So for every server I add to the system, I get another X thousand kind of concurrent users, concurrent requests of throughput. So theoretically then I can scale this up as much as I want, and if I want to double the number of users, I just double the number of databases. That's what happens with web servers, and that's what we want to do here. However, if we end up splitting the data between servers, i.e. by sharding it, then we end up with the danger of having to join tables in other databases. So again, we incur not just a network latency, but we're still tying up connections to the database server other than the one we've actually connected to. So we're not really solving the problem. And duplicating the data and saying, well, why don't we just have 50 copies? Well, again, that's great, but if they're both writable, that replication is either going to, again, increase connections and network latency or going to cause stale data. So that's kind of the difficult bit, and that's why it can't really be automatic in a normal sense of things, because there's more information here, more decisions that have to be made in order for us to actually set up something like this that's going to work. So the question is, well, how does it work in NoSQL? So if you go into Cosmos DB in Azure, which is their NoSQL engine, you'll find that it has this bold claim about its, global scale database, scale out as far as you want. And in fact, unlike the geo-replication in SQL Server, which allows you to have only 4 read-only replicas, with NoSQL, you can have as many replicas as you like. You can have one in every single data center in the whole world. And why is that? Well, the reason is very simply that NoSQL doesn't have those relationships between the data that SQL has. So effectively, as in this example here, I can have the customer with ID of 500 in the left-hand server, and I can have the customer with ID 100 in the right-hand server. And then in my web application, if my query is for customer 100, then the client library knows to send it to the right-hand server, and that's the only server I need to go to. I pull back that document and I have everything you need. What happens in NoSQL if you have something like a salesperson linked to the customer? Well, you kind of got a couple of different options. You could have a kind of a different server with a different database, different NoSQL database set up for salespeople and users. Or you could do a query that joins more than one server and kind of take the hit where you need to take the hit. But something else you can do, which is more acceptable in NoSQL than it is in SQL, is to denormalize the data. So in this example, you can see the salesperson called Luke is the same salesperson in both documents, but rather than using a symbolic link of some sort that we would use in a relational database, we've simply duplicated that data into both of those records. Obviously, there's a danger that if we want to update the details for Luke, we're going to have to update them everywhere. But that's a design decision that might be acceptable. But by doing this, we end up managing to avoid either the synchronization or the cross-server joins. And really, this is sharding. This is what sharding is, and sharding is the kind of the only real way we're going to get this elastic scale. Aha, you say, but what about SQL Server sharding? Because I've heard of that before, and I think that's been in SQL Server for probably at least 15 years. But actually, sharding in SQL Server isn't quite what it sounds like. It's actually a disk level sharding rather than a server level sharding, and really it was designed for a time when disks were mechanical and, relatively speaking, were very slow compared to RAM and CPU. So what would happen is on every database server it would always be the disks that would be the performance bottleneck, and disks were only so fast. They were literally spinning plates. And what people used to do was start building disk arrays and say, well, if we set up an array of 8 disks and we can get SQL Server to speak to 8 separate disks, then I'm going to get 8 times the disk throughput. And as long as I can balance the data between those disk shards, then I can try and make sure that I'm getting almost as much increase in throughput as I am adding disks. So SQL Server sharding was designed for that. They haven't increased it really to do kind of server level sharding or what we might call NoSQL clustering or sharding, which is a shame. But again, I think it's because there are a number of questions that can't be answered automatically by SQL Server, which are things that you have to decide and you have to implement in order to make sharding work for you. So this kind of brings us to probably the closest we're going to get to like a kind of truly elastic database scale out mechanism, and it's called the Azure Elastic Database Tools. Now, confusingly, this is not anything really to do with an Elastic Database pool. An Elastic Database pool is a collection of databases that share the resource that you're paying for, so that you can allow, you know, peaks and troughs in performance usage to be offset against each other. So it's purely a pricing convenience and is nothing really to do with scaling. Azure Elastic Database Tools are a set of tools to allow you to design databases that can be sharded effectively and can give you the kind of the throughput that you're looking for. Now, this is kind of an example of what this might look like. So in this case, I've used an example of one Elastic pool that has two databases in it, and then a standalone database which could potentially be a different size, a different performance tier. And that's perfectly acceptable, because the issue with Elastic tooling, the Elastic tools that come from Azure, is it's not actually a built-in piece of functionality for Azure at all. It's something kind of not really anything to do with SQL Server engine at all. What the tooling is a mechanism that sits above a collection of databases that allows you to pretend that they are a cluster of database shards. But effectively, it's an abstraction layer. It isn't any fundamental engine mechanism. So in the example of this one, like I say, I've got a single pool and standalone database. You can have any combination of those. It doesn't matter if the databases are kind of different sizes, except, of course, if they get full up and then you need to do something to it. You could have multiple pools, multiple standalone databases, and it kind of really depends on, you know, what kind of setup you've got for your application, whether you have a handful of very large customers or, you know, a much higher number of smaller customers. But really the setup doesn't really matter, because the abstraction layer will hide all of these databases from you and will kind of give you the functionality you need to connect to the right one. And because this works, or is designed to work largely in the same way as NoSQL, it avoids as much as possible the cross-shard joins that you would normally have to do in a SQL database. Now, this doesn't actually prevent you from doing that, so you do need to have some design input to make sure that you design your system correctly. But theoretically, in the best case, I will only ever have to hit one of these database instances. So as I said, it's not a portal thing. What you actually get when you get the tools is you get a management service, which is basically a downloadable cloud service. And then you get the Elastic Tools client library, which is available for Java and .NET. So effectively, you build that library into your application, and that's what gives you the library functions to be able to get the right connection to ensure that you're connecting to the right database. The management service is only required if you're ever splitting and merging data. We'll look at that a bit at the end. But if you are just kind of creating shards and putting data into them, pulling them out, you only need the Elastic Tools client library. And that side of it is relatively easy to use, but unfortunately it isn't magic. It doesn't do it all for you. So we're going to go through some steps to kind of show you what this actually looks like. So step one is really to choose your sharding key. Now, the key is really any unique piece of information. It doesn't actually have to be completely unique, but information that's unique enough that can decide which of these database shards a particular record is going to go into. So let's say you had 10 large customers, or that kind of number of large customers, and you kind of think, well, I just want one database per customer. Well, then that's dead easy, because your sharding key will be the customer ID. Customer 1 might go in the first database, customer 2 in the second one, customer 3 in the third one, etc. And if you've got a high cost product, then perhaps they're paying you enough money that you don't care about kind of creating a new database just for that one customer. You add it to your shard map and then it just kind of works. So that's one way of doing it. The other way of doing it is you could say, well, I've got a couple of big customers. So let's say in this picture here, these two large databases are for two banks that I do work for. They pay more money, so they can have a database to themselves. But actually then I want to put everybody else in that last database because everyone else is much smaller. So you can obviously set things up like that. So you're looking really to try and think in terms of your throughput requirements. Who is using the system? Who's using it the most? Are all customers using it equally? Are some customers using it more than others? Because really that's what you're trying to match with the throughput of the databases. If you have two customers that account for 50% of all the traffic on your website, then you probably want those two customers to have a database each to give them maximum throughput. And then probably everyone else can either have, one or two databases or whatever. So you can choose a customer ID or a user ID. You could even kind of go globally as well. So if you're, for instance, you have a global application where you're selling stuff to people in different countries, maybe it makes sense to have the sharding key as the country code. So that means everyone in the USA is in one database, everyone in Britain is in a different database, etc. So depending on your application, you got to think who's using it the most, what makes most sense. How am I going to put this data in a way that means I'm not going to end up either with one massively overused database shard, and especially if you've used something like country code, how do you split that down again when you've used country code as the sharding key? Because if everyone's in the USA and you filled up the database, you're kind of a bit stuck. So you need to think about that carefully, but that's a conversation that you and I can have later if you want to pay me some money. You've also got to consider what happens if you have a user that's, let's say, related to a customer. So all that means is, let's say customer one has a load of users. We need to design it so that all of those users and that customer are all in the same shard. So when I'm dealing with that customer and its users, I'm always dealing with one shard. Again, trying to keep those queries to hit a single shard and not have to query all of them. Of course, if you've got the kind of many-to-many relationship with, say, users and customers, then you've got to consider the right way to do that. You might have to accept a cross-shard query as a performance hit. If that's relatively infrequent, that might be okay. You might consider copying tables into all of the shards as reference tables, so all the users might exist in every database. So you've got kind of a couple of issues there, but understanding it well enough in advance means you can make those decisions before you've built your application and not trying to make it fit afterwards. So step one, choose your sharding key, because that's how we're going to kind of do stuff going forwards. Let's just say in our case we'll choose customer ID. And step two, so like I say, you don't have to create an elastic pool. Generally it's probably going to be cost effective because by definition you're going to be creating multiple databases, so why not get them to share a single pool of paid resources rather than having some doing nothing at some points and others doing a lot of stuff. So probably that's a good idea. Creating the elastic pool is pretty straightforward. When you create it, you have to create a server at the same time or choose an existing server. But the server being in the pool doesn't really mean very much by itself, because when you add databases to the server, they don't automatically go into the pool. So I'm not quite sure why you have to create the server for the pool, but you do. So there you go. It's called when you click add new resource, it's called SQL Elastic Database Pool. So that's the one that you have to choose. You don't have to set up very much to get it up and running, but the pool, you'll have to select how much you're going to pay for it. And just a quick note, the pricing tier for the pool starts at a higher level than it does for individual databases. So I think the lowest number of DTUs you can have in a database, I think, is 5 DTUs a second. And for the pool, I think it's 50. So it's a lot higher, but obviously if you're creating 2, 3, 4, 5 plus sharded databases, then that 50 is split between all of them. So just so that you know that. So that's step two, you created the pool. Now, step 3 kind of depends on whether you've already done this before or you're doing it from scratch and this is the first time you've done it. So if this is the first time you've done it, I recommend downloading the example app. The link is there, but if you just find the documentation for Elastic Database Scaling in Azure, you'll find the link to this example app. It's on MSDN. And it's effectively a console app which allows you to kind of connect your stuff on Azure and do some of the basic operations. And it's kind of quite cool to have a little play with this because it allows you to look at what happens and, you know, kind of get an idea of what all the different databases and stuff are for. It will also be an important kind of basis for your own management app. So what this app does, as an example, you will have to do for real. So where this says, you know, add another shard or even create the shard map manager, you're going to have to do that yourself for your application. And the way that your application adds another shard is not going to be necessarily the same way that this adds another shard. So but by having this example application, it allows you to kind of see the basic building blocks of what happens. The good news is once you've actually set it up, using it is a lot more straightforward. So we'll see some examples of that in a minute. When you download the app, you have to edit app.config and it will ask you for your Elastic server that you've just created, and also obviously username and password and stuff like that. Also ask you what kind of tier of database you want to create. So it's set to basic by default, which is the cheapest, which is fine. But obviously if you're using it for real, you need to change that. And when you hit option 1 on this, it will literally create 3 databases. One of them will be the shard map manager. There's only ever one of those. And that's the one that just knows what the shards are, what type of shard it is. Is it by range or is it a list of items? And then this will also add 2 additional databases for 2 separate shards. And they will be for integer ranges by default. So I think they have 0 to 100 and 100 to 200, I think, are the default shards that it adds. And in this case, it uses a customer ID as the sharding key. So when you run this, what you'll need to do is you'll need to unlock when you create your SQL Server, you'll need to unlock the IP address that you're running this console app from. Otherwise, you try to connect it. Obviously, the firewall won't let it connect. But once you've done that, you can kind of hit option number 1 and it will kind of run those things. But just a quick note that I found a bug in this where it creates the database using SQL by running it on the actual server, but then immediately tries to run a SQL script on it to create the database schema. And Azure's not quite ready for that to happen, so you get an error when you try and run that script in the code. So what I did was I added a thread.sleep for 10 seconds after it's created the database, just to give it time for Azure to realize that it has been created before it runs the database creation schema. So I'd recommend that you add that in. But the schema that it runs, the SQL script it runs on the database, it doesn't do anything special for it, for either the Elastic pool or for the Elastic kind of tooling. It literally is just a database schema. So a lot of this is not really specific to Elastic, because each of these ultimately is just a separate database with the same schema on it. So once you've done that, if you go back to Azure, you'll then see something that looks a little bit like this. So there's the server I've got at the top, and then the shard map manager and 2 shards. Now the thing is, now you can actually connect to this using SQL Server Management Studio, which I recommend doing, just to open it up, have a look at what's in, say, the customer table. And then if you go back to the console application and run option 3, it will insert sample rows into those databases. Every time you press 3, it will only insert 1 row. So you need to run that multiple times and it will just pick a random thing to insert. So you can do that, and then you can use the query in SQL Server Management Studio again, just to look at the fact that only one of the databases has that data in it. So that's kind of where you'll get up to, and this will give you a kind of idea of what's happening here. Adding the database, you do it via the tool, but even if you did it yourself, you're literally creating it moving it to the Elastic Pool if you're using Elastic Pool, and you do that from inside the Elastic Pool. You click on it, you click, I can't remember, manage databases or something, I think it's on the overview screen, and then you can choose the databases and it will move them out of their own payment plan and into the pool. Creating the schema on the database, so that's not going to happen automatically, so create all your tables and stuff like that, and then updating the shard map. So you could do that in your own management app. You could create the database manually. You could then automate the shard map update. So obviously you can do kind of a mix of those using manual and automatic steps, but this is kind of where you get up to. The next step then is adding data to the databases. So if you have an existing database, that's a little bit trickier. What the easiest thing to do is to set up the existing database as if it was a single shard on an Elastic kind of database, a little bit like we've just done, but just add your one database to it, and then tell the shard map manager that you've got one shard that covers the whole range. Then you'll have to go through the pain and trouble of setting up the split merge tool to actually split that then out into multiple shards. Or you might say, well, the existing database is okay as it is, but I just want any new customers to go into a new shard, in which case you could set up your shard map manager to say, well, customer 0 to current maximum customer is in shard 0, and then anything from that up to the next boundary needs to go into shard 1. So you've got some kind of options there. Obviously, if you don't have any data, if this is a new application, then you just create an empty database with one or more shards, put the schema onto it, and then obviously connect up your application, and then you're kind of away. So last couple of slides, really just some examples. This is what it looks like when you then query data from a shard. So there isn't really a lot to it. The SQL code inside the brackets is the same as any other SQL code that you might use. There's nothing special there. The only difference is where you get the connection from. So you get the shard map from a shard map manager, and the shard map manager should be created once in your kind of application startup code, and it's thread safe, so everyone accesses it, and effectively then you get the map from the manager and store the map, and then you get the connection from the map. And effectively all this is doing is saying, well, you've given me the customer ID, and that's the sharding key, so I'll work out which of the shards that would go to from my little data map, and then I'll return you one of the connection strings, or the actual connection itself rather than the string. And so, and then you just use it as normal. So it's really not very difficult. One thing you do have to be careful of is if you're querying data, let's say you're querying a user, but that user belongs to a certain customer, well, then you still need to pass in the customer ID to get the correct connection, because otherwise the users that are stored with that customer, it's not going to be able to find them. So if you know the users belong to a customer and you know they exist in a certain shard, or users or anything else that belongs to the customer, then make sure you specify the customer ID, because again, this is the optimum solution. This goes to one shard and it expects to find your data there. The second example is, well, what happens if I want all of the data, or count all of the customers, or get all of the users for all the customers, those kind of things? Well, again, not particularly much more difficult. You get the shards from the shard map again, but this time you get all of them, and then you pass that to this multi-shard connection, and using that, again, you just do all of the usual stuff you do for your SQL connection string, create command, set it up, execute it, and you're away. Notice that there's a couple of extra options that might be relevant here. So you can set it to include a shard name as a column. So when you get back, you say, well, this user came from shard 1, but this other user came from shard 3. If that's relevant to you, you can include that automatically. Or if you actually don't want to wait for all of the shards, if you had 100 shards and 2 of them time out, you might kind of say, I don't really care, I'll happily get partial results, happily to get a decent set of results rather than no results. Then you can set that as the execution policy, and if some of them time out, then you get back most of the data that it could get. So the actual code in terms of using it in your app is really very straightforward. The setup is a little bit icky, but even more icky is splitting and merging data. So what we've had so far is relatively straightforward. If you have no data currently, then you can do what we've already done. You can set up your shards already. You can start using them. You can add a new shard quite easily. You don't have to do anything clever there. But if we ever have to split a shard that's become too large, or merge shards that we kind of think, do you know what, we've got 5 here and they could all fit in one, then you have to kind of go down this road of setting up the split and merge tool, which is a bit old and a bit nasty. I get a sense of which it's something that might have been set up several years ago and given out to us to use, but it's not really at the same level of quality as most of the other tooling, which is a shame. So I'm not going to go into it in details, just to say it's a tool that runs separately from the main client library, as you might imagine. So there's obviously some concerns about data integrity during the operation of splitting and merging. So they're all mentioned in the documentation, so you can find out about that, but you need to think about that. But if you need to do this, I'm just going to give you the kind of overall, kind of list of things. So when you set up, you download some NuGet packages. That's where you get the stuff from. You create a database, so you're going to have a status database, which is effectively going to keep track of knowing what's been split and what's been merged. And the service uses that while it's splitting, and it kind of keeps track of what's going on. And obviously you then need to enable Azure access to that if you're going to run the cloud service on Azure, which is kind of set up for by default. So you then create a cloud service for the tool. The only thing I don't know is, can you convert the cloud service just to run maybe as a local service or as an app service or whatever else? Answer, I don't know. By default, it's set up as a cloud service. There's probably not a good reason for that anymore, but unless you want the extra headache of doing that, you're better off just doing it the way they recommend, which is create the service. Follow the instructions for modifying it. So effectively, you're going to have to modify the service configuration.csconfig to put in your credentials, etc., etc. Then there's a whole load of kind of security stuff. It's obviously wants to run over HTTPS. They talk about creating a self-signed certificate, etc., etc. You might be able to work around that if you already have, for example, a wildcard certificate. You could possibly hide the cloud service behind a CNAME and do it that way. But again, I haven't set this up and I don't really want to, so I don't know. Then deploy what you've set up and configured, so it's now up and running. There's some PowerShell scripts they use to test the operation. So the PowerShell script will talk to your web service that you've just deployed and make sure it can kind of see everything it needs to see, create shards, delete shards, merge, split, all the rest of it. And then you need to open your shard map. So the shard map you might have already created earlier. You obviously need to allow your cloud service to access that. So you're going to have to get the IP address of your cloud service and make sure it can talk to it, and obviously set up the credentials for the cloud service to talk to the database as well. And then you either go to the service by using the web portal, or you can use PowerShell scripts. Depends a little bit on whether this is something you're going to automate or not. So using PowerShell, the PowerShell talks to the web service, so you still need to use the web service. And then the web service then talks to your shard map manager and does all the splitting and merging. So kind of a bit icky, but there you go. So that brings us really to the conclusion here, which hopefully has been fairly obvious as we've been going along. Scaling up SQL databases is relatively easy, but is limited. There's only so far you can go and can be quite costly as you get towards the higher end. But scaling out is hard. A number of options we have. Read-only replicas are pretty easy, but they only really give you read capacity. Read-write replication can be complicated, but it's doable using data sync or using just any other kind of replication tool. You then have the difficulty of making sure that the right data gets updated. And no cloud providers really provide any true elastic functionality, because the tools is the closest you can get. But as I said, the tooling is really a set of libraries and an abstraction layer. It isn't anything fundamentally built into Azure or SQL Server. And the tooling is quite basic, it's quite clunky. There will be a reasonable amount of effort to set it up and understand it, Probably at the same time, once it is set up, you're probably not going to need to change it very often, so it might be worth the investment. But currently, the only thing I can really see happening is I could potentially see Microsoft kind of building some of this tooling directly into the portal. I don't really see it happening anytime soon, so it's not great. But at the same time, if this is the closest you're going to get to any decent scale out functionality for SQL Server, then this is probably your best bet. Your only other alternative is to go wholesale over to NoSQL, where a lot of these problems go away. NoSQL is much easier to scale out on Azure and probably on the other providers as well. But moving from SQL to NoSQL is not a 5-minute job. There are some problems with doing it, some issues that you'll need to design for. So that is another option, but probably something best avoided for now. So thank you, cotswolditconsulting.co.uk. If you have any questions about the video, please put them below. That's fine. Any professional kind of inquiries or anything you want me to work with you on, please contact me via the website and we can have a chat about that separately. Thanks very much.